Okay, this is a presentation about solubility, more about solubility, and some solubility rules. So up until this point, we've probably assumed that all ionic compounds are soluble in water, but as it turns out, some ionic compounds are not very soluble in water, to the extent that we generally just say that they are insoluble. And there's some simple rules that will get you a ways down the road if you know them in terms of predicting the outcome of chemical reactions. So let's talk about some factors that affect solubility generally. Temperature affects the solubility of solids. Generally, as temperatures increase, the solubility increases for solids. There are a few odd solids out there like calcium carbonate that become less soluble as the temperature is raised, which leads to some problems. For instance, if you have a hot water heater, and I imagine that you do in your house, whether it's electric or gas, that if you have hard water coming into your home, that as that water is heated, the calcium carbonate starts to basically lime up your hot water heater. So it precipitates inside your hot water heater, and eventually it builds up to such an extent that the poor hot water heater just dies. For gases, generally, they're going to become less soluble as temperatures increase. You know that from just having a soda pop, that if you leave it out on the counter and as it warms up, it's going to become flat because the carbon dioxide that gives the soda its fizziness is becoming less soluble in water or in the aqueous solution. Pressure also affects the solubility of gases. Along with your warming soda, you've relieved the pressure on the can, so there's less pressure of the gas above the solution. So as that pressure decreases, the solubility of the carbon dioxide also decreases. I was talking about some general solubility rules, and this is kind of how I'm going to organize the table. Our book used to have a table like this, but then they've kind of changed this. I kind of like this kind of a table format here. The general order of considering rules are first, the things that we consider soluble. We're going to start with box number 1 here. So if it contains lithium, sodium, potassium, ammonium, nitrate, or acetate, then we're going to consider the salt completely soluble in water. So we would expect it to ionize completely and form an equivalent amount of ions in solution. It's a little bit trickier with chloride, bromide, and iodide. Almost all of them are soluble, with a couple of exceptions. Silver ions, lead ions, and mercury +1. And it's kind of an oddball here. You never find mercury +1 by itself. It's what we call a dimer. So we've got 2 mercury +1 ions that are hanging on to each other, but if they bump into chloride, bromide, or iodide, they're going to form a solid. So there's my unless. I forgot my unless animation here. So sulfate is the same way. Almost all sulfates are going to be soluble. That's rule number 3. Unless I find sulfate in the presence of barium or lead ions. So those are going to form a precipitate. They're going to form a solid and settle to the bottom of your beaker. And then the last rule are the insolubles here. Carbonates, sulfides, oxides, hydroxides, phosphates. They're generally insoluble, so almost always insoluble, unless we find them paired up with rule number 1. So lithium carbonate or sodium sulfide, potassium hydroxide, ammonium oxide, or something like lithium phosphate. Those would all be soluble compounds. So we're going to play a little game here of soluble or not. And the first one here, I've got sodium sulfate. I'm a little worried about sulfate, but I know that sodium is under rule number 1 as soluble, so I'm expecting that to be soluble in water. Next along, oops, I hit the button too quick here, but silver nitrate. So I know there's a rule about silver, but nitrate is also in box number 1, so that makes it soluble. Lead carbonate. I know there's a lead rule, but when I look up carbonate under rule number 4, carbonates are generally insoluble unless they appear with one of the group number 1 ions. So I'd expect that to not be soluble. So no, I don't expect lead carbonate to be soluble. Silver iodide. So I go down to row number 2, there's where I find iodide, and silver is one of the exceptions, so I expect silver not to be soluble. Ammonium sulfide. Ammonium is an always, so it's always soluble no matter what, even if it is with one of those insoluble ions like sulfide, so I'm expecting that to be soluble. Copper 2 hydroxide. So there's no rule for copper in the first column, but I see that hydroxides are generally insoluble. So that must mean that copper hydroxide is insoluble. So no, not soluble. One thing we can do with these rules is predict the physical state of products in a double replacement reaction. So you all know how double replacement reactions, they're the partner trading. So sodium and silver are going to get new partners in the first reaction, so I'd expect sodium to pair up with nitrate and silver to pair up with chloride. And that's what we get, and then we have to figure out what the physical states of those are. So sodium is an always, and so is nitrate, so I'd expect that to be soluble. And the thing we do with something that is soluble in water, we write AQ, which is the abbreviation for aqueous, and aqueous just means dissolved in water. Now silver chloride, silver doesn't have its own rule, but chloride has a rule that says that silver is one of the exceptions, so silver chloride should be insoluble. So insoluble means that it's going to form a solid and settle to the bottom. So the physical state for silver chloride would be solid. Calcium chloride and potassium carbonate, partner trading, I get calcium carbonate and potassium chloride. When I figure out the physical states, there's no rule for calcium, but carbonate ions are generally insoluble, and calcium isn't one of the exceptions, so that must mean that it forms a solid. Potassium is an always soluble substance, so I expect potassium chloride to be soluble, so I'm going to write AQ. Let's see, lead nitrate and sodium iodide. Partner trading. Lead is going to pair up with iodide and sodium with nitrate. I'm going to come back and get that all balanced there. So lead iodide. I know that iodide has some rules and lead is an exception, so I'm expecting that to form a solid and settle to the bottom as an insoluble species. Sodium and nitrate are both always soluble, so I can write AQ, meaning that they're dissolved in water. Sodium chloride and calcium nitrate, partner trading. Sodium nitrate and calcium chloride. When I consider their solubility, sodium and nitrate are always soluble, so I write AQ. Calcium chloride is also going to be soluble, so I can write AQ. Now, as it turns out, if both my products are aqueous and my reactants were also aqueous, then what I have is a no reaction. So that would mean that no reaction actually happens in that last one, even though we can kind of write it out. The ions would stay floating around in solution. They don't want to gather up and form a solid with each other, no matter what ions are present there, sodium, nitrate, calcium, or chloride. One way of illustrating this is something called a net ionic equation. So net ionic equations, every book on the planet does it wrong. Basically, there are two ways to write these. There's my way and the wrong way. So this is one of those cases where my way is best. The way that most books do it is overly complicated. What I do is I transfer down anything that is a solid, liquid, or gas. So in this first reaction here, I've got silver chloride, solid. So I'm going to bring that down. And then I just ask myself, which ions went into making silver chloride solid? And the answer would be silver ions and chloride ions. And then I look up at the original reaction and confirm that I had sources of those. So the silver ions came from the silver nitrate and the chloride ions came from the sodium chloride. So I feel fairly good that I have a good net ionic reaction. And if I can write a net ionic reaction for a partner trading reaction like this, then I can say that the reaction is going to happen. Remember that last reaction I said that it wouldn't go? Well, net ionic reaction would show that. Oh, I forgot that the ions that don't appear in the reaction are called spectator ions. So sodium and nitrate would be spectators in that first reaction. The second reaction, when I try to transfer down solids, liquids, and gases, all I have is aqueous there, so I can't transfer anything down. And if I can't transfer anything down, then I have no reaction. Simple as that.